Hi everybody, I'm Martin Pirringer. I'm a mentor for FRC team 1989, and we have set out to 3D print First Robotics robot. The questions I'll try to answer is, why do we use 3D printing? What we used before 3D printing, what were the challenges, and what are the challenges using 3D printing for First Robotics style robot. Okay. Before that we had all metal design. You need a lot of metal working equipment which we didn't have. We just had some hand tools. The advantage is very sturdy, it's very heavy. We always had problems making weight. We had to sometimes not use certain features that we wanted to put on the robot to make weight. So weight was always a problem. Poor accuracy is hand tools. And it's expensive, was too expensive for us to set up and maintain a machine shop. Okay? The challenges with 3D printing is you have to get your material selection right. The first parts we tried to print in PLA, but PLA is not a good material for mechanical parts. It's too brittle, it breaks too easy. It's nice and hard and stiff, but it shatters. The second is you have to design this plastic in mind. So there's a completely different mindset when you switch from metal to plastic. Okay. Plastic bends easier. It is sometimes it's more flexible. Sometimes it's that is a good thing sometimes because you can bend and it bends back. Like nylon, it's almost indestructible in this situation, but it's not very stiff. Sometimes you want stiffness, sometimes you don't. So sometimes you have to create a hybrid. Yeah? That's then when you integrate these metal components, which we sometimes do. And the workflow for us was, because we were working with hand tools before that, it's just put stuff together as they went along, grab a piece of metal, put it here, drill a hole here, put them together, you know. Now everything has to be designed, okay? So, we're talking about the PLA is okay for like little switches, you know. ABS and HIPs are good working plastics. ABS we don't like too much, it stinks a lot when you print it, and who knows if those fumes that come off it, if they're toxic or not. Yeah? HIPs, a little tiny bit. HIPs is great for, it's great inexpensive, it's great for gears, has good wear pattern at low speeds. It doesn't wear much at all. It's very stiff, and you can hit it pretty good and it won't break. It's nice to print and it's cheap. PETG is a little bit more flexible, okay, than HIPs, and it's not that good for gear because PETG likes to stick to things, but it makes a great material for some motor mounts and some brackets. And then the king is nylon for a lot of this stuff. It's a little bit tough to print. You need an all-metal hot end. You should have an enclosure for that, and you have to print slow. I can print HIPs at 18.5 cubic millimeters a second, nylon at about 8 cubic millimeters a second. That is less than half the speed, so it takes twice as long. And then in some cases, flex makes sense, like for tires, rollers, and things like that. When you design for 3D printing, you have to have in mind, which you don't have to do with metal, which way is the torque going to run? Okay, which way is the forces going to go? Because 3D printed parts are stronger in the direction of the layer of the 3D printing layers than cross layer separation. They're only about 60 to 65 if you're doing good percent strong along the layers. So they usually tend to break along the layers. You need to keep printability in mind. Can the item be printed when you design it? And you have to make sure it can. So you want to cut down on the need of supports for the item, because supports need cleanup, supports leave things over. So when you, for example, make gears, you want to design your gears that there's no supports, otherwise you're going to do a lot of cleanup, because you always get a little bit of material left on the support. And then we have to incorporate off-the-shelf items, like maybe a gearbox, maybe a motor. In some cases, we insert a metal bracket inside the 3D printed part to make it stiffer, give it some different properties, or to interface with an off-the-shelf item. Okay? Then you have to select a CAD program. We in our club we use Inventor because the school teaches it. There are plenty of other CAD programs around there. And we do everything in that. We do involute gears, we make all kinds of brackets. I mean, you can check out the robot and where we have it. You have to pick a train extrusion for using the 3D printer, and you have to slice. We're using slick 3-iron crucial slicer. The reason why we use slick 3-iron crucial slicer is because if you want to print fast, and that goes into the next item, nozzle selection, most of our stuff we print with a 0.8 nozzle. Now you get into, if you print it too fast, you have poor extrusion. An example, for example, is hips, which is the fastest you can print. You can print at 18 cubic millimeters a second. If you print an outside layer or an inside layer at 1.5 millimeter width, 4 millimeter height, that comes out to 0.6 cubic millimeter per millimeter printed. At 18 cubic millimeter, the maximum speed you can print it at is 30 millimeters a second. Now the printer can handle more than 30 millimeters a second mechanically. So if you set it at the standard speed of a 40, 50 or 60 millimeters a second, you're going to have a very inaccurate and crappy print, and that's why a lot of people say you cannot print accurately with a 0.8 nozzle. Okay? Now at crucial slicer or slick 3R, you have a field that is maximum volumetric extrusion rate. Yeah? You put in the 18 cubic millimeters, or it's about 13 for PLA, 12 for PETG, about 14 for ABS, and that's on the V6, that's on my printer. If you want to, we have on GrabCAD a tutorial how you can figure it out accurately on your printer, at your temperature, at your print settings, what the best extrusion rate is for your material. Because you get maybe a protoplaster or printed solid, you're going to get a different extrusion rate. We have a different extrusion rate of nylon for a 910 from Talman, or bridge nylon from Talman, or a CX12 from Hobby King. They have all different extrusion rates. Yeah? And you establish the extrusion rate at your temperature, at your printer, and then you just enter it, whereas in something like Cura or any other slicer you use, you're going to have to, for each layer or infix section, you have to go to the advanced section, you have to calculate the speed out for yourself and hope you get it right. Wrong button. Okay. Now, and then for us, very important is budget constraints. That is one of the other reasons why we use hips a lot. It's because we can buy it for between $8 and $10 a kilo, which is much cheaper than most other things. So usually everything we print first in hips. Last year we went through about 70 kilos for hips, And if it breaks in hips, then we print it in nylon. So it is, unless the stuff that has to be printed in PET, into G. And then, of course, when you know what material you're going to print in, unless you already have a printer and modified, that will then determine what printer you get, and so will the size of the printer be determined on what you want to print. In our case, a robot has a lot of big parts, we want a big print. We currently use the Vernon, which is a 400 by 400 by 450 millimeter printer for that, so a big format printer. And if you do nylon, you want to go to an all metal hot end. And you have to make sure whatever printer you get, like for hips, you need a 100-degree bed. Nylon, you need 90-degree bed. So your bed has to be able to get up to the heat that you want to print at. Okay? And that is my basic presentation. I would like to hear now if anybody has any questions. Yes.
Have you found that moving to 3D printing instead of traditional means of making robot has opened up the imagination of the students a bit and can branch out more creativity?
Oh, I think it has done a lot because it has moved us away from making things as we go along. It has forced the students to sit down and plan it out first. Okay? It has made us more CAD-driven, so it has made the whole workflow more professional, which is good for the students. And it has the students they are more excited about. That's what I found. There's a greater level of excitement because it seems to be more satisfying to take the stuff off the printer than to drill a hole in a piece of Anglo aluminum. That's just how it seems to be. I don't know why, but they're very, cool print.
So how do you determine if your flow rate is too high? This is something that I have to try to quantify for my company, and I'm still struggling with it.
Okay, I will give you the tutorial. You can download it in GrabCAD, look for FRC 1989, but here's the basic flow. Do you have something like pronter face or something where you can send commands to the printer?
Yes.
Yeah, okay. You start off G1 E50, which is extrude 50 millimeters, or in pronter face you can select extrude 50 millimeters, and then a speed. The speed is F, let's say 180. The 180 is 180 millimeters a minute. Yeah? You start off at a value that is guaranteed low. I start off with usually 180, that's 3 millimeters a second, yeah? And 60 for flexibles. Yeah? You look at the extrude, what comes out of the nozzle. Yeah? And it should be nice and even. If you have a bottom tube, the end is going to tape off a little bit, but you save that piece. Now you increase the value, you get G1, E50, F240, yeah? And look at the extrude. At some point, it's going to start to look different. It's going to be either fatter or blotchy, or you're going to start to hear the gear of the extruder skip, click, 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 click. Yeah? Now you know where you went too far. Yeah? So let's say that happened to you at 420. Yeah? So 360 was the last good value. Now if you're running 1.75 millimeter filament, and through cross section, as the diamond is 1.75, half of that is 0.875 squared times pi times 1, so 1 millimeter of filament has 2.4 cubic millimeter volume. Yeah? So now at 360, you divide that by 60 to get it, because the printer wants it in millimeters a second. Yeah? So there is 6, that would be 6 millimeters a second, times 2.4 is 14.4 cubic millimeters. Yeah? I deduct 10% of that to come to a safe value, because I don't want to print just at the edge. I want to have a little safety margin. So that would be for that filament 13, which is a good average value for most PLAs. Yep. So now I know my extrusion rate at, let's say, 220 degrees on my printer is 13 cubic millimeter for that brand of filament. A different brand is going to have a different extrusion rate, most likely. Now, if you have bruiser slicer or slick 3R, you just put this in maximum extrusion rate and you're done. Yep. If you don't, right, let's say you print with a 0.8 nozzle, let's make easy math, 0.8 nozzle, 1 millimeter layer width, 0.4 millimeter layer height. Yeah? So 1 times 0.4, it's roughly rectangular, the bar that you extrude would be 0.4 cubic millimeter per millimeter extruded. Yeah? So if I take 13 and divide it by 0.4, I come up with about 32.5. I don't have a calculator here. Yeah? So the maximum speed for that setting would be 32.5 millimeters a second. Yeah? And that's the big mistake that people sometimes do. They say, oh, I go to a 0.8 nozzle, I can print 4 times as fast. Maybe, depending on what filament and what speed you printed before. You know? But most likely, no. That's why, in my opinion, a 0.8 nozzle is about the biggest nozzle up to a volcano. Maybe not on a super volcano, I've tried it. Not tried it, but up to a volcano, that makes sense. Yeah? Because even at hips, at a volcano, you probably got to be printing max speed at 60 millimeters a second, and that is what most printers can handle. You know? Any other questions regarding that? I have it all written down on brand cap.
Okay. I've got one follow-up question.
Okay, so I understand how to calculate the length of filaments and volumetric, but I guess my question is, are you looking for, assuming your extruder is not skipping or you're having some artifacts due to the shortcoming of the printer itself, are you looking for die swell specifically coming out of the nozzle?
Yeah, I mean, you're going to see it when you go too fast. The extrude is going to get shorter. Yeah? So if you lay them down on the, I usually take the 50 millimeters, whatever comes out of it, lay it onto the build plate on the desk. I put the next one next to it, looks about the same, very close. The next one is 3/4 the size.
Okay, so it's drastic.
Yeah, so it's thin, or it gets on some filament, it becomes pearly. It's like a string of pearls. You have like little of unmelted, especially with a big nozzle like a 0.8, you have little pieces of unmelted filament in the middle. It only melted the outside. So now you have like pearls coming down, you know? So now you know you went too far. What I usually do after that is I tune my extrusion multiplier. I have designed an E, where the first letter of the line of the E is 1 millimeter, the second 1.25, the next one 1.5, 2 millimeters, and then 3 millimeter on the edge. Yeah? And I print that out and then measure with a caliper. Yeah? And now you can get down, if you get close to the pre-designed values, you know you have your extrusion multiplier right, and most likely good layer adhesion. If I print a 2 millimeter line and it comes out at 1.8, yeah, then I have under extrusion. Then I have to maybe have the flow rate right, but I still have under extrusion. I gotta up the extrusion multiplier. If I come out with 2.5, then I have over extrusion. Yeah? So usually you want, like, I shoot for like 2.02, 2.04, a slight over extrusion, and then I correct for that in my designs. Like I put a backlash into my gears to take care of that difference. And then you print the test gear. If you want to print gears, you print the test gear and see how it measures. And make the final adjustment. Any other questions? Okay, I guess that's it then. Thanks for listening.